Last time we saw how to express the running time of merge sort as a recurrence relation, and how we could solve that recurrence relation to give a big O upper bound. In this video, I want to consider a wider range of recurrence relations to give us practice with both our techniques for solving recurrences, and to give us a sense of the sorts of running time analyses we can expect for our recursive algorithms. To begin with, I've rewritten our recurrence relation for merge sort in a way that lets us focus on the more important constants by de-emphasizing some of the others. And I've also color-coded the different parts of the recurrence so we can think about how those would generalize to other recursive algorithms. In our merge sort recurrence, the running time for a problem of size n depended on the running time for a problem of size n over 2, because the recursive calls to merge sort were on arrays of half the size. And for any divide and conquer algorithm, we will be calling our function recursively on smaller subproblems, but the size of those subproblems may not always be n over 2. Likewise, for merge sort, we had 2 recursive calls, which gave us twice the runtime on a size n over 2 subproblem. But for other divide and conquer algorithms, we might have a different number of recursive calls. Our merge sort recurrence also had a c times n term characterizing the running time of the merge step where we put together the answers that we got back from the recursive calls. But for other recursive algorithms, the amount of time that we spend splitting up into the subproblems or combining the answers from those subproblems may not always be linear. We also had a base case for the recurrence that took constant time, and this will essentially always be true for any recursive algorithm. The reason is that even if our implementation of the base case is extremely inefficient, say it took exponential time, when we evaluate an exponential function like 2 to the n on constant size input, like n equals 1 or n equals 2, we get a running time like 2 or 4 that we can always treat as a constant. So while we need to write down the base case of the recurrence for completeness, it will essentially always be big O of 1. So in a moment, we'll consider a number of different recurrence relations that describe the running time of other recursive algorithms you may have encountered. And those recurrences will differ from our merge sort recurrence in these 3 areas. In terms of the constant out front, that will always be an integer because it's based on the number of subproblems, but it might be 1 or more than 2. The term here describes the amount of work done on every call to the function, which includes any work that we need to do splitting up the subproblems before we make the recursive calls, and any work that we need to do recombining the solutions that we get back from the recursive calls. And we can consider lots of other running times for the rest of the function. We might have a constant or a log running time, or polynomials other than linear. The recursive portion of the recurrence relation that describes the size of the subproblem can in principle be any integer, at least 1, and less than n. But the common cases we should consider include splitting into subproblems that are not exactly half the size, but maybe some other integer fraction of the size, like n over 3 or n over 4. But we should also consider algorithms where the recursion operates on inputs that are only smaller by 1. To help give a sense of when we might see these different possibilities in a recurrence relation, I've written recurrence relations for several classic algorithms. I hope everyone has seen binary search before, where we have a sorted array and we're trying to determine whether that array contains a particular element, and so we'll go to the midpoint and use that to decide which half of the array we need to search in recursively. In binary search, much like in merge sort, a recursive call operates on half of the array, But unlike merge sort, we only have one recursive call in binary search because when we compare to the midpoint, we determine which half of the array the element could be in. And each time we call binary search, we do a constant amount of work outside of the recursive part. On the way down, we have to compare the element we're looking for against the middle element to decide which half we're recursing on, but that takes constant time. And on the way back up, we just have to return the true or false that we got from the recursive call. So when we draw a tree for this recurrence of binary search, we will have just one node at each level, and at every level we are doing a constant amount of work. And since there's one node per level and constant work per node, we also have constant work per level. And the number of levels is the number of times we have to split the array in half in order to reach the base case, and that's just log base 2 of the input size. And so to get the running time for binary search, we need to add up the work that is done across all of the levels. So we are summing up over all log base 2 of n plus 1 levels, the constant work done on that level, and so we get c times the number of levels. And once we have a solution to the recurrence, we can do big O analysis, and we get a log n running time. Next, I've given a recurrence for if we implemented selection sort recursively. When we saw selection sort before, we did it with an iterative algorithm, but we could turn that iterative algorithm into a tail recursive one, where each recursive call operates on all but the first element of the list after we have selected that first element. In that implementation, our selection sort on size n has a recursive call on size n-1, and there is only one such recursive call. But before we make the recursive call, we have to do big O of n work in order to scan the array that we were given to find the minimum element that we want to swap into the first position. When we draw a recursion tree for this algorithm, we will have levels for when we call our function on the size n array, size n-1, all the way down to the size 1 array. So we'll have a total of n levels, and on each level we have only one node in the tree because there is only one recursive call. But now the work per node is changing as we go down the tree because each time we go down a level, we are operating on a smaller array. So at the top level, we do c times n work to find the minimum of a size n array. Next level down, we do c times n-1. And on level I, we do c times n-I. And when we get to the bottom, we are operating on a size 1 array, which will just take constant time. And again, since we have one node per level, the work per level is equal to the work per node. Now again, we add up the work across all of the levels to get the total work done by the algorithm. Our index variable, which I'm now calling L to correspond to level, starts at 0 and goes up to n-1. And on level I, we do c times n-I total work. And this is probably a sum that you've seen before, but we can make it even more obvious by counting in the other direction, where we go 1, then 2, all the way up to n. And we can also factor out the c, and now we just have the sum of j from 1 to n, and we know that that's n times n plus 1 over 2. And now that we've solved the recurrence, we can do big O analysis, giving us an n² running time for selection sort, which happily matches what we found before. Here I've given a recurrence relation that corresponds to a much nastier sort of recursion. What I have in mind here is an AI planning algorithm that you might see in a machine reasoning class, where there's an agent who lives on a grid and needs to consider whether to move up, down, left, or right at every time step. And if the agent wants to make a plan for the next n time steps, then it has to consider each of those 4 possibilities, and then could recursively plan on a time horizon of n-1. So if we recursively plan on the n-1 time horizon, then we would have in our recurrence g of n-1. And if we need to separately build plans for what if our first action was left, or up, or right, or down, then we would have 4 recursive calls. And there's also some work that we need to do to actually evaluate each of those plans, but for now we'll suppose that that's constant time. So regardless of what's actually going on in the details of that planning algorithm, if this recurrence relation describes its running time, then we can build a tree to evaluate the recurrence. In this tree, at the top level, we have one call to the function on input size n, and it does a constant amount of work, which is all the work done at the top level. But at the next level down, we will have 4 recursive calls. We still do a constant amount of work per node, but now since there are 4 nodes, we are doing 4 times c total work at this level. As we continue, there will be n total levels until we get to the bottom. And on the next level, each of these recursive calls will make 4 recursive calls. So at level 2, we will have 16 nodes. Then at each subsequent level, we will have an additional factor of 4 nodes. And so at level I, we will have 4 raised to the I total nodes. We still do a constant amount of work per node, and so at the ith level, we do a total work of c times 4 to the I. And likewise, at the bottom level, we will have 4 to the n-1 nodes and c times 4 to the n-1 total work. Now to find the overall running time of the algorithm, we add up the work done on every level. So our sum will go from 0 to n-1. And on level L, we will do c times 4 to the L total work. We can factor out the c. And you are definitely capable of proving that this summation is upper bounded by 4 to the n. And then once we have an upper bound for the recurrence relation, our big O analysis says that this algorithm has exponential running time. Hopefully that's given you a bit more sense of some recursive algorithms we might encounter, the recurrences that describe their running time, and the resulting big O analysis of those recurrences. But now I'd like to take another step back and think about a more general recurrence relation that describes the running time of a wide variety of divide and conquer algorithms. This generic recurrence describes the running time of an algorithm recursively using 3 different constants. We have one constant corresponding to the number of subproblems, one constant corresponding to the size of those subproblems as a fraction of the original, and another constant describing the running time within each call to the function. Our recurrence for merge sort is an instance of this generic recurrence where a equals 2, b equals 2, and d equals 1. And our recurrence for binary search is an instance when a equals 1, b equals 2, and d equals 0. Of note, this recurrence doesn't capture every possibility we might be interested in. In particular, it does not cover recursion on size n-1 inputs. But for a large fraction of the divide and conquer algorithms we will study, we can describe their running time using some variant of this generic recurrence. A full analysis of this generic recurrence would lead us to what is known as the master theorem, but we're not going to spend the time to go into that level of detail here. Proving the master theorem would involve a very generic version of our substitution-based inductive proof, but rather than going into that extreme level of detail, we will take a first step in generalizing our substitution proof for merge sort, where we will consider the case of more than two subproblems. Our goal now is to solve this generalized version of the recurrence, where we have a number of subproblems A, and we're going to use partial substitution, which means that we need to start with a guess as to the form of the solution, but there are some unknown constants, k and d, in our guess. And really all we're saying by this guess is we think there is some polynomial that solves this recurrence. We don't know the degree of that polynomial, and we don't know the constant, but we're going to figure that out along the way as we build our inductive proof. And of course, we're not trying to solve this recurrence exactly, but rather give an upper bound. We want to prove that our bound holds for all input sizes n, so we start with a base case of n equals 1. So this imposes some slight constraints on what k and d can be, but we clearly have lots of choices available to us. As long as k is at least c, this will work. Now we want to prove inductively that if our bound holds on smaller inputs, it will also hold for n. So we'll make the inductive hypothesis that our bound holds for all inputs less than n, and we want to show that if that's the case, then it will also hold at n. We're now analyzing t of n, so we can start from our recurrence formula. And I've turned our big O of n into some constant times n. And our goal here is to eventually show that this is upper bounded by k times n to the d. To get here, we need to use our inductive hypothesis, which says that the bound holds on smaller inputs, including an input of n over 2. And if our formula works on n over 2, then the value of t of n over 2 is at most k times n over 2 to the d. So now the question becomes, what value of d can we pick to make it so that this is less than or equal to k times n to the d? Well, let's ignore the c times n term for now and just focus on making this term less than or equal to this one. Well, we can do some algebra here, canceling a k on both sides and an n to the d on both sides. And so, as long as d is at least the log base 2 of a, we get the upper bound that we need. But there's a problem, which is that we haven't yet dealt with the plus c times n term. So we need to somehow account for this. And here we're going to come back to a trick that I mentioned last time but didn't actually use, which is we can add something to our guess that is of lower degree and will go away in the big O analysis. Specifically, we can modify our guess to add a linear term, and as long as d is at least 1, that's not going to change our big O analysis. And that's a reasonable expectation to have, because when we analyzed merge sort, we got something that was bigger than linear. So when a is greater than 2, we have more subproblems of the same size as the merge sort subproblems, so we should expect only a larger running time. And so adding on a linear term here shouldn't change our eventual big O analysis. We'll call the constant on our linear term L, and that means we need to modify the various steps of our proof. This plus Lm term slightly changes the conditions on our base case. We now need that k plus L is at least c, and our inductive hypothesis now includes the linear term on the smaller input size. And that means when we plug in the bound from the hypothesis for n over 2, we also have to plug in our plus L times n over 2 term. And we also get some more leeway in the upper bound that we are trying to show at the end. Now our task is to pick an appropriate value of L, and if we can make this term at least this one plus this one, we will have shown our upper bound. We can again cancel out the ends. And we can do some algebra to solve for L, noting that the inequality flips on the last step because a is greater than 2. So if we pick d equal to the log base 2 of a, L according to the algebra we just did, and k equal to c minus L, then we have proven that this upper bound holds for all positive integer values of n. Importantly, our proof only works when a is greater than 2. If a is equal to 2, then our solving for L does not work. And that's good because we know that we shouldn't just get a polynomial for merge sort, we should get n log n. And for a less than 2, our bound would be correct, but it wouldn't be the tightest possible, because as we saw with binary search, we can sometimes get a logarithmic running time, which is better than any polynomial. But our result here is a really valuable one when we have more than 2 subproblems. Specifically, if we consider the cases of 3 or 4 subproblems of size n over 2, so if we have subproblems of size n over 2, but we have 3 subproblems, then we get a running time that is big O of n to the 1.6. Or if we have 4 size n over 2 subproblems, our running time is big O of n squared.